Okay, in today's lecture, we're going to start our section 5.2 material on infinite series. And that's going to be what we work with really for the remainder of this semester is infinite series and determining whether they converge or diverge and some applications involving infinite series. So let's start by defining a series. We would say that an infinite series is the sum of the terms in an infinite sequence. A(n) as n ranges from 1 to infinity. So in our last section, 5.1, we defined infinite sequences as an ordered list of numbers, and an infinite series is now the sum of those infinitely many terms. It is denoted by using a capital sigma. So we would say capital sigma of a sub n from n equals 1 to infinity, and this is used to denote the infinite sum a1 plus a2 plus a3 plus a4 and so on out to infinity. So we're adding adding the terms of this infinite sequence. Now, for any infinite series, we would define the partial sums of that series as follows. S1 would be just the first term of our series, A1. S2 is the sum of the first two terms of our series. S3 is the sum of the first three terms of our series, and so on. So in general, Sn is called the nth partial sum, and it is the sum of the first n terms of our series, which could be denoted using the shorthand sum from 1 to n of a sub I. Now, these partial sums that we're defining define a new sequence of terms s sub n, and this is called the sequence of partial sums. So the partial sums that we're listing out themselves could be considered as the terms of an infinite sequence called the sequence of partial sums. And we saw in our last section for any infinite sequence, we may or may not have a limiting value. We want to determine whether that sequence converges. So let's think about how we would define convergence or divergence for a series. So let's suppose that we have an infinite series of terms a(n) from 1 to infinity, and we're going to let Sn denote the nth partial sum of that series. So that is S sub n is the sum of the first n terms of that series. Now, if this sequence of terms, S sub n, is convergent and has a limiting value of capital S, then we would say our infinite series is convergent, and we write that the infinite series is equal to S. Now this number, capital S, is called the sum of our series, and if our sequence of partial sums does not converge, then we would say the series is divergent. So the way that we're really defining this infinite sum is as the limit of a sequence of partial sums. So the sum from 1 to infinity of these terms a sub n is really defined as the limit of the sequence of partial sums, S sub n, as n becomes large, and recall that S sub n was the sum of the first n terms. So we're looking at the sum of the first n terms and then taking a limit as n approaches infinity to see whether this sum of infinitely many numbers is converging to a sum or diverging. So now that we've defined these things, let's look at some examples to get a little practice with these infinite series. So in our first example, we are asked to find the first 5 partial sums for the series n equals 1 to infinity of 1, and then we ask, does that series converge? So let's start by finding our first 5 partial sums. starting with S1, the first partial sum, which would just be the first term of my series. Now in this case, every term of our series is defined as a constant 1. So S1 would be the sum of just the first term, which is 1. Then S2, our second partial sum, is the sum of the first two terms. So here we would have 1 for the first term and 1 for our second term, since it's defined as a constant term 1. So our second partial sum would be 2. Our third partial sum would be 1 plus 1 plus 1, or 3. Our fourth partial sum is the sum of the first 4 terms, which are all 1, so we have 4. And S5 would be the sum of the first 5 terms, which again are all 1, so we would have 5 for our fifth partial sum. Now here we're asked about whether this series is converging, so let's think about the nth partial sum. Based off the pattern that we see emerging, we would probably say that the nth partial sum would be equal to n. So to determine convergence of our series, sum from 1 to infinity of 1, we would have the limit as n approaches infinity of s sub n, which is equal to n, and this limit does not exist. The values are diverging towards infinity. So here we would say that the series from n equals 1 to infinity of 1 diverges, since the sequence of partial sums is diverging towards infinity. So let's look at another example. In this next one, we have got a similar problem. We're asked to find the first 5 partial sums for the series n equals 1 to infinity of negative 1 to the nth power, and then we ask, does that series converge? So let's start by listing the first 5 partial sums. Here, the first partial sum, S1, would be the first term of our series. So plugging in n equals 1, we have negative 1 to the first, or just negative 1. S2 would be the sum of the first 2 terms. So for n equals 1, we had a negative 1, and then we're adding, when we plug in n equals 2, we get a positive 1, so we're left with 0 for the second partial sum. Now S3 is the sum of the first 3 terms. That would be a negative 1 plus 1, and then when we plug in 3 for n, we have a minus 1, so we get negative 1. Then S4 is the sum of the first 4 terms. So we had a negative 1, plus 1, minus 1. And when we plug in 4 for n, we get a positive 1. So we're again left with 0. And then S5 is the sum of the first 5 terms. So negative 1, plus 1, negative 1, plus 1. And for n equals 5, we get a negative 1, so the sum of the first 5 terms is negative 1. And we see a pattern emerging here. So in general, the nth partial sum is defined piecewise. It's either negative 1 if n is odd, or 0 if n is even. So we see that our sequence of partial sums is an alternating or oscillating sequence, and there is no one number which it is approaching as n gets larger. So in this example, we can say the limit as n approaches infinity of s sub n does not exist, So the series that we were given from n equals 1 to infinity of -1 to the n diverges, since our sequence of partial sums was not convergent. So let's look at another one. In this next one, we are considering the series n equals 1 to infinity of 1 over 2 to the n. We are supposed to show that that series converges and find its sum. So as we did in the first couple of examples, let's start by finding the first few partial sums and see if we can find an expression for the nth partial sum. So in this example, starting with our first partial sum, plugging in 1 for n, we have 1/2. For our second partial sum, we would have the sum of the first two terms, so 1/2 plus, if we plug in 2 for n, we have a 1/4. For S3, we've got the sum of the first three terms, so 1/2 plus 1/4 plus 1/8. For S4, we have 1/2 plus 1/4 plus 1/8 plus 1/16. And if we simplify these terms, let's see what we have. For S1, we had 1/2. For S2, 1/2 plus 1/4 is 3/4. For S3, we have 3/4 plus 1/8, which gives us 7/8. And for S4, we had 7/8 plus 1/16, which leaves us with 15/16. So the pattern we can start to see emerging here is maybe a little more easily described if we rewrite the form of these partial sums. So for S1, which was 1/2, we could think about this as 1 minus 1/2. For S2, we had 3/4, which we could think about as 1 minus 1/4. For S3, we had 7/8, which is 1 minus 1/8. And for S4, 15/16 can be thought of as 1 minus 1/16. So in general, our pattern here for the nth partial sum could be described as 1 minus 1 over 2 to the nth power. So to determine whether this series converges or diverges, we would look at the limit of this sequence of partial sums, which is described as 1 minus 1 over 2 to the nth, as n gets larger, and this term, 1 over 2 to the nth power, as n becomes large, is approaching 0. So we're left with the limit of a constant 1, which is 1. So here, our series, the sum from n equals 1 to infinity of 1 over 2 to the nth power is equal to 1. So we would say this series converges with a sum of 1. Okay. So in these first few examples, we're seeing that one way that we could try to determine the convergence or divergence of a series is by listing the first few partial sums, seeing if we can recognize a pattern for the nth partial sum, and then take our limit. So let's look at a problem that's sort of working in the opposite direction. Here we are told to suppose that the nth partial sum of an infinite series from 1 to infinity of terms a sub n is given by S sub n is equal to n plus 1 over 2n plus 4. And we're asked to find, for part A, the sum of the first 5 terms of our series. Now the sum of the first 5 terms is given by the fifth partial sum. So if I have an expression for the nth partial sum and I want the fifth one, I'm going to plug in 5 in place of n. So we'll have 5 plus 1 over 2 times 5 plus 4, which leaves us with 6 over 14, or 3 over 7. So the sum of the first 5 terms of our series is 3/7. And then in part B, we're asked if our series converges or diverges, and if it converges, we want to find our sum. So to find the sum of an infinite series from n equals 1 to infinity of terms a sub n, well, it's defined to be the limit of the sequence of partial sums, s sub n, as n becomes large. So in this example, we have the limit as n approaches infinity of n plus 1 over 2n plus 4. And either by using L'Hopital's rule or by comparing the coefficients for the highest power of n in the numerator and denominator, we get a limiting value of 1/2. So in this example, we would say that our series converges with a sum of 1/2. Now in part C, we ask for A1 or A10. That is, for our series that we're given, we don't know what the general term is for A sub n, but we do know the nth partial sum. So we're asking in part C for A1, and to find A1, well, we know A1 would be the first term of our sequence, which is the same as the first partial sum. So here, to get S1, we would plug in 1 for n in our nth partial sum, and we have 1 plus 1 over 2 times 1 plus 4. So that leaves us with 2 over 6, or 1/3, for the first term of our series. Now we're also asked for A10. That is the 10th term within my series. So to get A10, well, one way I could do it would be to take the 10th partial sum, that is the sum of the first 10 terms, A1, A2, A3, up through A10, and then subtract S9, the sum of the first 9 terms, A1, A2, up through A9, and that difference leaves me with the 10th term in my series. So here, S10, if we plug in 10 for n, we have 11 over 24 minus S9, if we plug in 9 in our formula for S sub n, we have 10 over 22, and this reduces to 1 over 264 for the 10th term in our series. Now, in the last part of this example, part D, we want a general formula for A sub n. That is, we want to know for this sequence what is the formula for this A sub n term that we're adding, describing the nth term in my sum. So just like we did in part C, when we were asking for, say, A1 or A10, if I want a general term for a sub n, I could take my nth partial sum, Sn, and subtract the n minus first partial sum. So I'm taking the sum of the first n terms and then subtracting the sum of the first n minus 1 terms, and that leaves me with just that nth term a sub n. So what we have here, if we look at S sub n, we have n plus 1 over 2n plus 4, and then we're subtracting S sub n minus 1, which would be n minus 1 plus 1 over 2 times n minus 1 plus 4. So if we simplify a little bit, this leaves us with n plus 1 over 2n plus 4 minus n over 2n minus 2 plus 4 gives us 2n plus 2. And then if we want to simplify a bit further, we can try to combine these fractions by getting a common denominator. So here my first term was n plus 1 over, if I factor out a 2 from the denominator, I have n plus 2 minus n over, if I factor out a 2 here, I'm left with n plus 1. So for the term a sub n, if we want a common denominator, we could use the product 2 times n plus 2 times n plus 1. And my first fraction, in order to get that common denominator, I would have to multiply the numerator through by n plus 1. So I would have n plus 1 squared, and then minus my second term. In order to get that denominator, I would have to multiply the numerator n by n plus 2. So we have, if we expand our numerator, n squared plus 2n plus 1 minus the quantity n squared plus 2n, all over 2 times n plus 2 times n plus 1. So that leaves us with just a 1 for our numerator over 2 times n plus 2 times n plus 1. So in this last example, if we have the nth partial sum of our series, even if we don't know what the terms are, we can use that nth partial sum to answer questions about convergence or divergence, or find an expression for a sub n, the general nth term in my series. Now, what we're going to start looking at throughout the remainder of this chapter is different ways to determine whether a infinite series will converge or diverge. For most of the series that we work with, it won't be easy to find an expression for the nth partial sum. So we're going to start talking about different tests for convergence or divergence. And the test that we use will depend on the type of series we're working with. So we're going to introduce a few different types of series and tests for convergence or divergence. And the first one that we're going to talk about is what's called a telescoping series. So here I will start by defining what is a telescoping series. So here is our definition. A series is said to be a telescoping series if there is some internal cancellation in the partial sums. So that definition seems a little bit tricky. What do you mean by an internal cancellation in the partial sums? Well, let's look at some examples of telescoping series, and I think that helps explain the definition. So in this next example, we are given some series. We're asked to determine whether it converges or diverges. And if it converges, we want to find the sum. And if it diverges, we want to explain why it diverges. So in part A, we have the sum from 1 to infinity of cosine of 1 over n minus cosine 1 over n plus 1. So we see that these two terms in the general expression for our series involve cosine of 1 over n and cosine of 1 over n plus 1. So these terms appear like they might cancel one another if we start listing out the partial sums of this series. So let's start by writing an expression for the nth partial sum. So the sum of the first n terms. So here I'll start by plugging in 1 for n, and I would have cosine of 1 minus cosine of 1/2. Then we would add the next term of our series. So if we plug in n equals 2, we would have cosine of 1/2 minus cosine of 1/3. Plus, if we write the next term in our series, plugging in n equals 3, we have cosine of 1/3 minus cosine of 1/4. And we're going to keep listing these terms until we get to the nth term. That is cosine of 1 over n minus cosine of 1 over n plus 1. So we see if we write out our nth partial sum that some of these internal terms are going to cancel each other. In this example, our minus cosine 1/2 and plus cosine 1/2 cancel. The cosine of 1/3, our next term, this negative cosine of 1/4, is going to cancel with the next term that we wrote out, which would be cosine 1/4 minus cosine 1/5. And these terms will keep canceling. And then for this last term, our cosine of 1 over n will cancel with the term just before it. If we plugged in n minus 1 for our sequence, we would have a negative cosine of 1 over n for this previous term, which will cancel that cosine of 1 over n. So we're left with only the first term and our last term for this nth partial sum. That is, S sub n is given by cosine of 1 minus cosine of 1 over n plus 1. So this is the nth partial sum, and to determine whether this sequence converges or diverges, we look at the limit as n approaches infinity. So here, taking our limit, we have our first term as the limit of a constant, cosine of 1. And then as n becomes infinitely large, this 1 over n plus 1 term decreases to 0, and we're left with cosine of 0, which is 1. So we've got cosine of 1 minus 1. So in this example, we say the series sum from 1 to infinity of cosine of 1 over n minus cosine of 1 over n plus 1 converges with a sum of cosine of 1 minus 1. All right. So here, this first example illustrates why we're calling it a telescoping series. These internal series are collapsing on each other or canceling each other out, and we're left with just a few terms in the partial sum, which we can then take a limit of to determine convergence or divergence for the series. So let's look at another one. In part B, we have the sum from 1 to infinity of log of n plus 1 over n plus 2. And if we were to write out the first few terms of this partial of the sequence of partial sums for this series, it doesn't look initially like the terms are canceling each other. But what I can do in this example is make use of a property of logarithms. So recall that the log of a quotient can be rewritten as a difference of the log of the numerator and the log of the denominator. So here, if we rewrite this, this is really the sum from 1 to infinity of log n plus 1 minus log n plus 2. So if we were to write out the first few terms in our nth partial sum, we start to see that this is a telescoping series. So our first term in the nth partial sum would be, if we plug in 1 for n, natural log of 2 minus natural log of 3, plus, for the next term, if n is 2, we have log 3 minus log 4, plus, for the next term, we would have log 4 minus log 5, and so on, until we get to the nth term, which would be the natural log of n plus 1 minus the natural log of n plus 2. So we see here that the internal terms are canceling, or log 3, log 4, log 5 will cancel with the next term, and then up through this nth term, where log of n plus 1 will cancel with the term just before it when we substitute n minus 1 into the term of our series. So again, we're left with just the first and the last term of our series, or of this nth partial sum. So we have s sub n is equal to natural log of 2 minus the natural log of n plus 2. And to determine convergence or divergence for our series, we take the limit of this nth partial sum as n becomes large. So here, log 2 minus log of n plus 2. So as n becomes infinitely large, log of n plus 2 becomes infinitely large. So I have log 2 minus this infinite quantity is diverging towards negative infinity. So here we would say the series diverges, since the limit of the sequence of partial sums s sub n did not exist. So let's look at some other ones to illustrate a few more complicated cases for these telescoping series. In part C, again, when we look at this series, it initially appears like it might not be telescoping. But if we were to rewrite this general term, 1 over n times n plus 1, using a partial fraction decomposition, we see that this is in fact telescoping. So here, the form of the decomposition would be a over n plus b over n plus 1. So to solve for a and b, we could multiply through by our common denominator, and we have 1 is equal to a times n plus 1 plus b times n. So to solve for a, if I let n equal 0, the equation becomes 1 is equal to a. And to solve for b, if we choose n as negative 1, the equation becomes 1 is equal to negative b, which implies that b is negative 1. So the series that we're given, that is the sum from 1 to infinity of 1 over n times n plus 1, can be rewritten as the sum from 1 to infinity of 1 over n minus 1 over n plus 1. So by performing this partial fraction decomposition, we see that this series does appear to be telescoping. Now, if we write out the first several terms in the nth partial sum, we would have a first term of 1 minus 1/2. If we plug in n equals 1, so 1 minus 1/2, plus for the second term in our series, we would have 1/2 minus 1/3, plus plugging in n equals 3, we have 1/3 minus 1/4, and so on, until the nth term, which was 1 over n minus 1 over n plus 1. So again, we see that these internal terms are canceling. Our plus minus 1/2, plus minus 1/3, this negative 1/4 will cancel with the plus 1/4 in the next term, and our 1 over n cancels with the term just before it, when we plugged in n minus 1. So we're left with the first and the last term in our nth partial sum, and we have s sub n is equal to 1 minus 1 over n plus 1. So to determine convergence or divergence, we take the limit of this 1 minus 1 over n plus 1 as n becomes large, and we see that we are left with a limiting value of 1. So the series converges with a sum of 1. Okay. Now in our last part of this example, part D, we have the sum of 7 over n times n plus 2. So let's see how this one works out. It looks sort of similar to what we saw in the previous example. So maybe we could again try a partial fraction decomposition. So we could take 7 over n times n plus 2, and its decomposition would have the form a over n plus b over n plus 2. So to solve for our coefficients, we could multiply through by the common denominator, and we have 7 is equal to a times n plus 2 plus b times n. So to solve for our constants, if I want to solve for a, if I choose n as 0, our equation is 7 is equal to 2a, which implies that a is 7/2. And if I want to solve for b, if I choose n as -2, the equation is 7 is equal to -2b, which implies that b is -7/2. So if we look at our series, that is the sum from n equals 1 to infinity of 7 over n times n plus 2. This is the same as the sum from 1 to infinity of 7/2 with a positive 1 over n, and then minus 7/2, so I could factor out the 7/2, 1 over n plus 2. Or if I want to pull the 7/2 out in front of my summation, I'm left with 1 over n minus 1 over n plus 2. This looks very similar to the previous example, but we notice one difference in this one from the problems that we've considered in the earlier parts of this example. So these terms which are appearing to cancel each other now lie 2 units apart. So previously, all of the terms which were canceling each other were differing by 1 unit, say 1 over n minus 1 over n plus 1. Here we have 1 over n minus 1 over n plus 2. They're a little further apart in the terms that are going to cancel each other. So we've got to be a little bit careful here when we think about our nth partial sum. Let's go ahead and write it out. Here, the nth partial sum, s sub n, will be given by a constant 7/2 times the terms of this series. Now the first term of my series, if n equals 1, is 1 minus 1/3 plus the second term would be 1/2 minus 1/4 plus 1/3 minus 1/5 plus 1/4 minus 1/6, and so on. And if I write out the last couple of terms, if I plug in n minus 1, I have 1 over n minus 1 minus 1 over n plus 1, and then plus, for our nth term, 1 over n minus 1 over n plus 2. So let's see which terms will cancel here. We see that our minus 1/3 will cancel with the positive 1/3, negative 1/4, and positive 1/4. Negative 1/5 will cancel the next term that would appear after this negative 1/6. My negative 1/6 will cancel with a later term of a positive 1/6. And in my last few terms here, everything will be canceled except for the terms, the last 2 terms, 1 over n plus 1 and 1 over n plus 2. All of the other terms, this 1 over n minus 1 and 1 over n, will cancel with the terms that appear earlier in that nth partial sum. So in this example, where our subsequent terms which are canceling each other are 2 units apart, we would have s sub n involves a few more terms than what we previously saw. So we have a 7/2 times, well, we're left with, let's look at which terms we're left with. We have a 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. So here we're left with 1 1/2 minus 1 over n plus 1 minus 1 over n plus 2. So to determine convergence or divergence, we would look at the limit of this sequence of partial sums as n becomes large. So we've got our 7/2 times 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. And as n gets large, these last 2 terms decrease to 0. So we're left with a 7/2 times 1 plus 1/2, or 3/2, which leaves us with 21 over 4. So here our series converges with a sum of 21 over 4. So these telescoping series, we see we can find an expression for the nth partial sum by writing out the first few terms of our nth partial sum and seeing which internal terms will cancel. And depending on the form of our series, we're left with maybe just the first and the last term for my partial sum, or as we saw in this example, we were left with the first two terms and the last two terms in this sequence of partial sums. But once we find our partial sum, we can take the limit as n becomes large to determine convergence or divergence and find the sum of our series. So in the next part of this section, we will discuss other types of series, geometric series, and determine methods for their convergence or divergence.